Hello everyone, Assalamu alaikum. Welcome back for another video in the series. In this video, let's generalize the concept of logistic regression to multiple classes. Previously, we have seen for binary classification case. Now we will see how we can implement this using multiple classes. This is also known as Softmax regression, or sometimes also called multinomial logistic regression. So for this, we will consider a relatively simple dataset, the MNIST dataset. We've talked about this before as well. So there are 60,000 handwritten digits in the training set, and it's a nice and balanced data set. Balanced means that there's the same number of training examples per class. So in this case, we have 10 classes, the handwritten digits 0 to 9, and there are 6,000 digits per class. Now here's an example of how these digits look like, and each of these on training example here has an image dimension of 28 times 28 times 1. So 28 for the height and 28 for the width. So this is the number of pixels. We have a total of 784 pixels of features per training example. In PyTorch, we will be using a format called NCHW, which is how we represent a mini batch or an image batch. So here in this case, we have 128 examples in that mini batch. So the 128 is for this in here. Then we have the color channel. We have only one color channel in this case because these are black and white images. So there are no red, green, and blue colors. And then we have the height, 28 pixels, and for the width we also have 28 pixels. This is usually how we read the data in this data set into PyTorch, and we will be also looking at code examples for that. So just to recap, at the bottom here we have 60,000 training examples and the corresponding labels, and then we have for the test images and test labels 10,000 each. So that's just how the data set looks like. For softmax regression, we will actually be concatenating these images or these features in the image to a long vector. We will see that shortly. So here's just an example of how kind of diverse these handwritten digits are. So these are all number 7 illustrations of different sevens. So different people writing down a 7, and you can see varies a lot. So but you can see also that just by looking at these handwritings, it's sometimes maybe not even clear what the number is. So if I wouldn't tell you that these are different illustrations of 7, some people might think that these might be ones or something else as well. Like I mentioned in the context of PyTorch, and when we work with unstructured data, also later with convolutional networks, we would be working with the format, the NCHW, as follows. So this would be a 4-dimensional tensor. Here's how it would look like in PyTorch, where we have this 4-dimensional tensor. Actually, in this case, it's a 3-dimensional tensor. I only represent one single image. So it's a single image here at the bottom, representing the number 3. And you can see there are different values from 0 to 0.5. I think the highest one would be approaching 1. And that is because I normalize these pixels by dividing them by 255. And this is because these values between or around 0, or in this case between 0 and 1, work better with gradient descent. It would be even better, for example, to normalize these images such that they are centered at 0. So you can, for example, subtract a 0.5. If you have the range between 0 and 1, you can subtract a 0.5, and then it would be ranging between minus 0.5 and 0.5. And this would work even better, or people say that that would work better with gradient descent because now it's centered at 0, and you can have positive and negative inputs equally. However, in practice, personally, for these simple data sets, I don't notice a big difference, especially if you work with logistic regression. Sometimes I put more effort into normalizing the input images, for example, doing the standard normal standardization, what people call the standard normal data. So it's giving your data the properties of standard normal distribution. But of course, if your data is not normally distributed from um, to begin with, it will also not be normally distributed after normalizing. So what I mean is, for example, if you have a given feature, you subtract the mean of the feature and then divide by standard deviation. So this would be called standardization, or some people just call that normal z-score normalization. This is also recommended. We can do that here too, but since the features are all equal, they are all from 0 to 255 for pixels, it wouldn't make a big difference whether we use this standardization or just scale them between the range minus zero point 0.5 and zero point 0.5. So that's like a minor detail. Now the main point here is what we are doing now is we are concatenating. So if I go back previous slide, we are concatenating the rows. So if you consider, fortunately there is a line wrapping here. If you consider this here as the first row, the second row, the third row, and so forth, if we concatenate these rows, we get a one long vector here, like so. That's how it looks like. So here I've concatenated these rows just to illustrate this again. Let me jump back one more time. So here's the first line of pixels in the image. This would be the first row. This would be the second row, and the third row would be this one. If we concatenate them, by that I mean if we make one long vector, we can use that as input for our logistic regression model. And in the case of MNIST dataset, we have more than two classes. So we are going to use Softmax regression. Now, just to briefly recap on before I introduce the Softmax model, here's a drawing of regular logistic regression model for binary classification case. So as input, we have a feature vector, and then we have this weight vector. So we compute the dot product between the two and add the bias unit, which gives us the net input. And then we put the net input through a non-linear activation function, the logistic sigmoid function, which we have discussed before as well. And then if so, what it represents is the probability. So this represents the probability that a training example belongs to class 1. If we wanted to compute the probability that it belongs to class 0, we would compute it as 1 minus the probability of class 1, right? This would give us the probability that it belongs to class 0. But back to this one here now, we have a probability and it belongs to class 1. And then we can say if this probability is greater, if p is greater than 0.5, then class 1, and if it's smaller than 0.5, then class 0. So how can we generalize this now to multiple classes? For that, we can actually extend this model. Now here's a drawing of model that would work with multi-classification dataset. So here's the drawing of a model that would work with multi-class classification dataset, where we have more than two classes. So just to jump back one more time, so this model here, this can actually be thought of as a model that is embedded in this bigger model here, like so. So if we have the same inputs here, it's the same as before our feature vector of dimensionality m. We can think of everything here as the same model that I showed you before, right? So this would be one logistic regression model. And for that one, we have a feature vector of dimensionality m. So if we have m features, we have this feature vector here, and notice now, I mean, we have multiple of these logistic regression models. The second model would be this one, right? So another logistic regression model, same inputs, and for this one we can have a feature vector. For this we could have the feature vector w21, w22, and so forth up to m. And then there's the third model here. For that, we have also a feature vector. We can write it as W31, W32, and W33, and so on. So if I call this feature vector, let's call it W1, and this is W2, and this is W3. So I have now three feature vectors. If I stack them, I can stack them to make a feature matrix. So this matrix here, I can write this matrix as I think I would need to transpose this. So we would have W1 transpose, W2 transpose, and W3 transpose. So this would be my feature matrix of the majority H times M, where H is the number of output nodes here. So this would be one way I could generalize my logistic regression model. And then we compute also the class membership probabilities here. However, notice now the class membership probabilities work a little bit differently, because we don't have a binary classification problem now, but each node is still binary. So here let's say this would be the probability that this class is 1. this is the probability that this is class 2. But now each probability works like this, that it is a probability that this is the class. So the probability that class is 3 versus not being class 3. So what can happen is that, or what will probably happen is that these probabilities don't sum up to 1. For example, for a given input, if we have the digit 3, we may get a probability that this is 0.3, or let's say 33%. That this class is 1. Let's say 40% that this class is 2, and then 70% that this is of class 3. But these don't sum up to 1. For example, if the probability is 40% that this is class 2, the probability that this is not class 2 would be 60%. And for this one, for the first one, the probability that it would be class 1 um, or does not belong to class 1 would be 67%. In any case, these probabilities don't sum up to 1. If we also take a look at this one, these don't sum up to 1. It can be a little bit weird. So if we have a number, let's say the digit 3 here, how can it be 33% number 1, 40% number 2, and 70% probability number 3? It doesn't really make intuitive sense. I think this would make sense if you have a data set where the classes are not mutually exclusive. For example, if you have something like a vehicle, there's a high probability that an object in an image is a vehicle. There's maybe also probability greater than 50% that this is a car, and then maybe a certain probability that it's a certain brand of a car, and so forth. So where we don't have mutually exclusive classes, but in case of digits, it would be more intuitive if these probabilities sum up to 1. And for that, we have this multinomial logistic regression model, or softmax regression model. So what I showed you in the previous case was more like a concatenation of individual logistic regression models. Here would be the real multinomial logistic regression model, where we assume that the classes are mutually exclusive. So what is the difference between this slide and the previous slide? So if I go back one more time, in the previous slide, we had one sigmoid activation in each node here. So I'm getting rid of this sigmoid activation and have a so-called softmax activation. And also notice that I'm drawing it a bit differently, because um, before I was drawing it inside here because they were all independent from each other. Now the softmax activation is actually not independent for each node. So all the activation go into the same softmax activation. And then there is some computation going on. I will explain to you how that works in the next video. And what comes out are these activations that now sum up to 1. So these all sum up to 1. So for example, the first one may be 10% probability that it belongs to class 1, then that might be 20% for class 2 and 70% for class 3, and so on. And how can we convert it into a class label? We would take an argmax function. So the argmax is the position, the index position of the highest value. If I scan these three positions, let's say position 1, position 2, and position 3, the highest index 70% would be 3. So this would return class label 3 if I apply the argmax. If this is unclear, we will walk through this step by step in the next video. So this was just the introduction of how the softmax regression model looks like. It's basically here the concatenation of individual logistic regression models. I hope this was helpful. If you have any questions, drop them in the comments box below, and I'll see you in the next video.